Good day. We bring to your attention a report on justification of the method of soil densification of the interstation tunnel by jet injection based on computer modeling. Poster 1. In underground construction to consolidate the soil base, silicatization technology has become widespread, in which a solution of calcium chloride and liquid glass with the addition of soluble chemicals, phosphates, aluminates, and bicarbonates, which promote gel deposition, are injected into the soil. As a result of the chemical reaction, a silicic acid gel is formed, which binds the soil particles into a strong and waterproof monolith. For injection of chemical reagents used injectors of different designs, differing in the type of perforated area and other design features. The injectors consist of solid steel pipes with walls up to 6 mm thick. In the lower part of the pipe are equipped with a conical tip, and at a length of 0.5 to 1 m have perforated links with holes 1.5 to 3 mm. The upper pipe is equipped with a special head for clogging and has a device for connecting the discharge hose. Poster 2. Chemical fixing has a number of advantages in comparison with other methods of fixing the soils of subway tunnels. Ease of work. Short terms of performance of works. The ability to consolidate the soil at any depth without the disclosure of any special workings and excavations. The possibility of conducting underground work without stopping traffic on the tunnel under construction. The disadvantages of this method include the impossibility of use in heavily flooded rocks and the toxicity of materials, which adversely affects the environment and the health of people working in the tunnel. Poster 3. To analyze the results of silicate consolidation and assess the positive effect of it, the graphs of subsidence of the tunnel frame structure and the results of geophysical monitoring at the site within PK230 plus 70, PK231 plus 00 between Sikorsky and Pozniaky stations on one track were studied. Poster 4. Monitoring of subsidence of the tunnel frame structure within PK230 plus 70, PK231 plus 00 was performed from the period of commissioning to September 2019. In the race between ART, Sikorsky, ART, Pozniaky carried out quarterly instrumental geodetic surveying observations of the height of the tunnels by laying the leveling course of 2 and 4 classes on the track benchmarks. The study of the experience of strengthening the foundations and the analysis of the results of consolidation allowed to establish that in the conditions of water-saturated state of the foundation soils it is expedient to use the method of jet cementation. Poster 5. Pozniaky station is shallow, has an underground hall with 2 landing platforms. The vault of the hall rests on a number of columns. The station hall is connected on both sides by stairs to the underground lobbies, which lead to the underground passages. Each underground passage has 2 exits to Mykola Bazan Avenue. The lobbies are connected by a gallery from which stairs lead to the station hall. The passenger traffic of the station is about 30,000 people per day. The construction of the station was carried out in an open way in the pit. The pit was fastened with wooden piles. All structures of underground passages, lobbies 1, 2, as well as the station are made of monolithic and precast concrete. Poster 6. In the section from PK237 plus 40.60 to PK239 plus 69.98 and from PK239 plus 79.95 to PK241 plus 10.00, the left and right distillation tunnels are built on one common monolithic reinforced concrete slab. To ensure the watertightness of the tunnel frame, pasting waterproofing on bituminous mastic is arranged. The distance from the ground to the top of the tunnel frame is from 2.2 m to 5.7 m. The slope for unauthorized runoff of groundwater and industrial water is 3 ppm. Poster 7. Koshkarov's hammer, ruler crack with an accuracy of 0.1 mm. Inspection of the technical condition of the tunnel frame was performed on the I and 2 tracks on the section within PK235 plus 80, PK243 plus 80 of the race of ART. Pozniaky, ART. Kharkiv Syresko Petcherska line. In addition, a survey of the surface above the tunnels was performed to detect dips and subsidence. Surface above the tunnels. During the visual inspection the following damages were revealed. failure of the asphalt concrete pavement of the car park up to 40 centimeters deep and about 6 square meters in the area of PK240 plus 73. Poster 8. Here you can see local subsidence of the surface above the tunnel with the formation of DIPs up to 20 centimeters deep. Poster 9. Here you can see one track, transverse cracks with opening up to 2.5 millimeters in track concrete. Locations of cracks indicating the size of the opening are given in the combined scheme of subsidence and damage. Poster 10. Here you can see a longitudinal crack in track concrete 4m long with an opening of up to 5 mm on PC241 plus 75. Poster 11. Here you can see cracks in the SSO blocks in the locations of the embedded part with an opening of up to 3 mm. Poster 12. Here you can see the filtration of groundwater through the joints of SSO blocks. Poster 13. During the visual inspection of the technical tunnel frame, cracks and crevices with opening up to 10 mm in the SSO blocks were found in the area of peak points, observed on the subsidence graph. Deformations of tunnel structures are mainly due to soil vibration creep. This phenomenon occurs due to the transfer of vibrodynamic loads from the rolling stock through the frame to the ground, while the base soil moving from the zone of vibration to the periphery causes subsidence of the tunnel structures. At the size of subsidence from 100 to 200 mm there are the first signs of deformations in the form of cross cracks in track concrete. At values from 200 to 300 mm, cracks appear in the locations of embedded parts, rigid joints, and gaps between the blocks. Further development of subsidence leads to an increase in the opening of cracks, track failure and to a decrease in the water resistance of the tunnel frame, which together affects the durability of structures. Poster 14. Below are the maximum values of tunnel subsidence, as of September 2018, within 1 and 2 tracks. Poster 15. As can be seen from the subsidence schedule, their development along the length is uneven and depends on the speed of trains, the lowest near the stations, the highest in the middle of the race, bearing nobility of base soils and the presence of organic impurities, location. The smallest subsidence is recorded in the areas adjacent to the station complex. Poster 16, 17, 18. Soil consolidation schemes. In the process of modeling the properties of soil cement material and geometric dimensions of soil cement piles were chosen as the most optimal for the given conditions. Jet grouting piles with a diameter of 0.8 m, a step of 1.8 m from the center of the axis and a calculated deformation modulus of 3000 MPa were used as fixing elements of the array. For the modeling process, 3 fastening options were selected with angles of inclination of 30, Poster 16, 35, Poster 17, and 40, Poster 18, degrees relative to the surface. The expected result of fixing should be considered: reduction of subsidence of tunnel structures, switchboard. Poster 19, 20. The calculation of the tunnel subsidence was performed by the finite element method in the Midas GTS-NX software package. Due to the impossibility of taking into account when calculating the phenomenon of vibration creep of sandy water-saturated soils, the values of sediments correspond to the actual static load, without the vibrodynamic component. For more accurate results, static loads were accepted with a factor of 1.3. According to the results of calculations, the following is established. 1. The amount of subsidence of the tunnel structures, namely the switchboard on which the SSO blocks are based, without the use of fasteners is 25.55 mm. 2. The amount of subsidence of the tunnel structures using fasteners at an angle of 30 degrees is 7.8 mm. 3. The amount of subsidence of the tunnel structures with the use of fasteners at an angle of 35 degrees is 8.19 mm. 4. The amount of subsidence of the tunnel structures using fasteners at an angle of 40 degrees is 8.82 mm. Poster 21. Analyzing the results of mathematical modeling, the most effective option was to fix it at an angle of 30 degrees, which allowed to reduce the subsidence by 70%. In order to save material and the total cost of construction work, was additionally developed and calculated option of fixing the soil with soil cement piles of reduced length, 10 m, at an angle of 30 degrees. Poster 22. Thus, reducing the consumption of materials by 40 to 45% managed to obtain only a slight increase in subsidence by 2.6% compared to the option with a length of 20.5 m and an angle of 30 degrees. Given the efficiency and economic attractiveness of this option, it was used to develop a startup project fixing the base of the subway tunnel with sloping soil cement piles of reduced length. The amount of subsidence of the tunnel structures without the use of fasteners is 25.55 millimeters. When fixed at an angle of 30 degrees, the subsidence was 7.8 millimeters, at 35 degrees, 8.19 millimeters, and at 40 to 8.82 millimeters. In order to save material and the total cost of construction work, an option of fixing the soil with soil cement piles of reduced length, 10 m, at an angle of 30 degrees was additionally developed and calculated, which showed its efficiency and economy compared to other options.